I just want to mention a few things. I'm sorry, in the last days I have a very bad allergy and my voice is still trying to recover. Yesterday I couldn't even speak at all. So I hope it's not going to be that tedious today. And the other thing is that what I'm going to show you today is the content of a 4 hours course. So I will try to condense everything in a very short period of time, of 1 hour. And for those who will be more interested in learning about these things, I'm gonna be teaching this course next month, somewhere in Colombia, and in July and September in Brazil. So if you are interested, you can let me know, and I'm gonna refer you with the organizers. So thank you. So okay, I'm gonna start now with. So the title of this presentation is introducing highly dimensional genomic and environmental covariance data into models for predicting complex traits. This is a research that I conducted when I was doing my postdoc at University of Alabama with Dr. Gustavo de los Campos. So back then, one of the issues that we had was many of the conventional statistical models were based only on main effects. And there was a boom of many authors proposing these models, and all of them claimed that their method was superior to the other ones, of course, in a specific data set. But in any case, one of the issues that we had back then was that there were not a model able to allow us to introduce the genotype and environment interaction in the models. So the outline of this presentation is first is a very brief introduction of what the problem of dealing with complex traits, what was the goal of this research. I'm going to present very quickly the statistical methods that were used back then, and then how we develop or derive the model that I'm going to present, the GI model. And then I'm going to present some data and data analysis and some results. And after that, we will move to very quickly to the practicals. Okay, as you know, many of the important economical traits are complex in the sense that they are affected by a large number of small gene effects. And these gene effects interact in many complex ways with the environmental conditions that the genotypes face in fields. So one of the challenges is how to cope with highly dimensional nature of genomic and environmental information, and how to capture this complex form interactions among large number of factors. And we can think about the problems in humans where we have personalized medicine, for example, trying to address these issues. So far, back then we had genetic data that was based mainly on molecular marker or pedigree, environmental factors that were not considered, and also interactions between these two. So back then, the standard genomic prediction methods consider the signal as the main effect based on molecular markers. But one of the issues that we faced there back then was that P, the number of molecular covariance, was larger than N, the number of data points for fitting the models. So some of the limitations is those models did not include these interactions or environmental data. And something that I want to point here is very quickly is that many authors have read papers that they address. Mewisen was the one who proposed the models for genomic selection. And I think, to be fair, the first one who proposed some of these models was Bernardo in 1994. And after that, Mewisen proposed the models that were able to cope with this high complexity of the data used for the record. So back then, there were two different types of approaches to deal with this complex data. One branch was the GWAS studies, where it was mainly focused on the SNP selection. And the other side, we had the whole genome regression that tried to use all of the molecular markers at the same time. And we had two different data types of data models, penalized and Bayesian. So, and they are similar in some ways, but also very different, specifically in the number of features that they allow you to include in the models. So the challenge of this research was to extend these whole genome regression models to accommodate highly dimensional markers, highly dimensional covariates, and interactions between them. So we will start very easy. Yesterday, I saw a little bit of the presentation. Dr. Rutkowski showed some of the things about genomic blob, and also in the morning, Dr. Lipka showed the equivalence with risk regression, at least in the Bayesian context. So in this case, we are dealing with a parameter. We are trying to find the optimal values of this parameter, but also we can induce a bias in this parameter. In this case, theta is the parameter we're interested. And when we induce a bias, we can reduce somehow the variability of this new parameter. So we are dealing with two things at the same time. So we are trying to reduce the variability, but also we are inducing a bias in this parameter. So these are the relations that we have to the shrinkage and penalizer methods. It's either a bias is induced by a prior distribution or a bias is induced by one of these L penalties. So let's start with a very simple model, a model where we are trying to explain the linear response of the phenotypic data of the phenotypic value as a linear combination between markers and marker effects. Some assumptions on the errors. So on the side of the penalizer regression, we have a problem where we are trying to somehow it's a trade-off between model goodness of fit and model complexity. In the other side, in the Bayesian regression, we have a prior for the effect of the markers. In this case, but when we check the solutions, we have they are somehow equivalent. So the solutions for the based on the penalizer regression is quite similar to the solution for the mode based on the Bayesian ridge regression. In this case, the one of the issues that we are trying to solve with either penalizer or the Bayesian regressions is we want to break the singularity of these metrics, because it's not full rank, so we cannot invert and get an easy response or an easy solution for these model terms. So what we are trying to do here is adding a small value in the diagonal, roughly speaking, to break the singularity, and it can be given by a penalty value or by a coefficient between the variance components of the model. In any case, here I'm still dealing with problems of dealing with high dimensional matrices, in this case of order P by P, because remember we have P markers. So an alternative parameterization, as was pointed yesterday and this morning, is the G-block model, wherein instead of considering each one of the marker effects, we can just put all of the information in one linear combination between marker and marker effects, assuming some normality again in the effect of the markers, in a way that when we stock the vector of genomic values as the linear combination between marker and marker effects, we have that by result of the multivariate normal distribution, this vector of genomic effects follows the expected value of this vector is centered on 0, with a variance at covariance given by x prime sigma square beta, where sigma square beta is the variance components associated for each one of the marker effects. And we can just traduce this very easily to G, with G as the kinship matrix based on molecular marker data. And these results are use the posterior model that, based on the Bayesian context, is a posterior model is equivalent to the blob of the G based on the frequencies approach. The only difference is that this penalty is given by the ratio between the variance components, between variance components from error divided by the variance components of the genomic component. Okay, so far we saw how it can be easy solve the problem dealing with high dimensional genomic covariates. So the next step is to add environmental covariates in the model. So assuming that in the same way that we can have a term explaining the environmental, the genomic value, we can have another explaining the environmental value. Well, in this case, W sub I represents the environmental value as a linear combination between environmental covariates and their corresponding effects. And we can assume, same as with genomic data, that these effects follows a normal distribution centered on zero and variance of covariance given by sigma squared sub gamma. Meaning we are assuming that each one of the environmental covariates has the same importance or same effect on the response. So following again the same tricks that we did for G-blob, we can end up with, if we stock all of the environmental values in a vector, we have the covariance of this vector is equal to W prime, where W is the matrix of environmental values, and is equivalent to omega, where omega is going to be some sort of environmental kinship matrix, where each one of the entries represents or describes the environmental similarities between pairs of environments. So now we have a model that includes main effect of the markers via covariance structure, main effect of environmental values via covariance structure. And again, the challenge is that we are dealing only with additive model. So it does not consider the interaction term so far. So in this research, we try to integrate the interactions between markers and environmental values in a similar way. So just remembering from our stats courses, the way how we proceed to include an interaction in a model is by considering the contrast. Suppose that we have two different data types, marker and environmental covariates. If we have two markers only and one environmental covariate, the number of contrasts that we have to include in the model is size number 2, so x1 w1 and x2 w1. If we have 2 and 2, we have to include 4. So one of the inconveniences is the number of contrasts grows dramatically. We already have issues trying to integrate main effect of the markers. Now imagine trying to integrate all of the interactions between each marker and each environmental covariate is going to be very, very complicated. A very small example now, we have 2,000 markers and 100 environmental covariates. The total number of contrasts to introduce in the model is 200,000. So no way that we were able to fit the model easily in that way. So for that, we developed this model for integrate the interactions using covariance functions. So assuming that we have two scores, one that describes the genomic effect with, again, similar to what we had before with the G-blob, B sub J following independent and identical distributed densities, and W another score, similar than before, following the effects, independent identically distributed densities. And we assume that these two scores are independent. It means the expected value of the genomic value is equal to the expected value of the environmental value is equal to 0. And the covariance of the II prime element is proportional to the II entry of the G matrix, and the covariance of the WI prime environment in genotype in an environment is proportional to the II prime entry of the omega matrix. So in order to consider a multiplicative model, we just have to consider the product between these two scores. So the only thing that we need to know in order to have a characterization of this model term is to know the covariance, the mean and the covariance function of this random effect. So we start in this way. So GW sub I is equal to the product between G sub I times W sub I. The expected value is easy because, as we saw before, we can separate these two components are independent, and the expected value of each one of these is equal to 0, so the expected value of them is 0. The covariance between the element GW sub I and GW sub I prime is equal to the expected value of GW sub I times GW sub I prime minus the expected value of GW sub I by the expected value of GW sub I prime. So we know by fact that this is equal to 0, so we just have to focus on the first part. But as we know, these terms are independent, so we can separate them and reaggregate in a way that this is equal to the expected value of GI times GI prime by the expected value of W sub I prime. And these are other than, these are just the II prime elements of the kinship matrix and the II prime element of the environmental kinship matrix. So this saves us a lot of complication because the covariance of this model term is proportional to the product between the I prime entry in one matrix times the I prime entry on the other matrix. So this is the product between cell by cell, considering two different covariance structures. So it's also known or called Hadamard product. So this new model term allows borrowing of information only between environment by line combinations that are similar genetically and similar at the level of the environmental covariance. And this is not new, I would say, or the model specification. It has some links with previous literature. So Coquelin and Kempton in 1954, they developed similar concepts when they show how to introduce the epistasis interactions in models using pedigree data. So now we have a model that includes main effect of the environments, main effect of the markers, and the interaction between each molecular marker and each environment. Okay, so one of the questions is, how should I put this in the context of the data that I'm working with? Because many times I have genotypes that are repeated in many environments, and what should I do in those cases? So when we are dealing with replicates, the only thing that we have to do is to expand the respective covariance structures that we are computing. For example, for markers G, suppose that we have 3 genotypes, but one of these genotypes is repeated, so in a different group. So what we have to do is to compute the incidence metrics in a way that the row where we have number 1 corresponds to the row of the corresponds to the group of the genotype. So in this case, we have group 1, group 2, group 3, and group 3. And the next thing is just compute the, assuming that we have a G matrix is of order 3 by 3 because we have only 3 groups. We have to expand these metrics in a way that we can add genomic data, assuming this simulated covariance structure based on genomic data to the individuals. So the only thing that we have to do is just to multiply Z, the incidence matrix, times G times C prime. And here, as we saw, the last individual is the one that is repeated in this from this group. And with this product, we are adding 1 extra column and with 1 extra row, and is similar to the 3rd row and the 3rd column. So we are just expanding the incident, the kinship matrix in this case. So far we review already a model where we are trying to introduce main effect of the markers, main effect of the environmental covariates and interactions. But sometimes we might need to bring a little extra information in the models. Why? Because it might be the case that there is imperfect linkage disequilibrium. The technology for sequencing is not perfect, or probably the current environmental covariates are not enough to characterize environments. So that's why one possible solution is to bring data from both sides. In this case, we are adding main effect of the lines in the model and the main effect of the environments in the model. Okay, so now I'm going to talk very quickly about the data and data analysis. So when we did this research, we got data from a French company where they gave us 7,000, around 8,000 phenotypic records, 139 with commercial lines tested in 340 trials or environments in France. So the total number of potential cells was 47,260. Only 24 cells have a replicate. Only 60% of the potential cells was observed, so this 7,000, and only one line was tested across all environments. So this is, roughly speaking, the experimental design of how the data looks like when we have environments in the x-axis and genotypes in the y-axis. Each one of the small black lines represents a line tested in an environment. Also, this data set has around 3,500 SNPs, and after we apply conventional quality control, we end up with something like 2,400. Also, we have initially 130 environmental covariates, but after we apply some quality control, we end up with 68. So we remove those with environmental covariates with more than 30% of repeated values and with more than 0.2% of lives. And these are the models that we compose. We consider models which have main effects and interactions. So in this case, we have models that include the main effect of the environment, lines, environments, markers, environments, weather data, environments, markers, and weather data, environments, markers, weather, and G/E. Without weather data, G/E, including weather data, and combining both types of G/E, with and without weather data. Also, we consider the variance components, and one of the questions is why we should consider this measure. And I think this morning, Dr. Lipka talked a little bit about what happened when we are using machine learning methods for genomic selection or GWAS. I really don't remember because I was in another meeting. I didn't see the whole presentation. But one of the reasons is because we can measure or we can assess easily how much of the variability is explained by each one of the different model terms. That using other alternative approach might sound a little more difficult to measure that. So that's one of the reasons why one of the first things that we look at always are the variance components. So let's say we have a model, we have a intercept, random effect of the markers, random effect of the environmental covariates. If we compute the expected value, these are centered on 0, so use the mean, but the variance, this term is constant, and these two terms are random. So the variance of y is equal to the variance of g plus, assuming these are independent, plus the variance of w plus the variance of e. So this is equal to the sum of the three variant components. So from here, we can assess how much of the variability we are observing in fields is explained by the genetic component, for example. So we divide this value, this variance component, by the total amount of variability that we are observing in fields times 100. So that's, I use a side note. Also, we consider different prediction scenarios. So one of, because we wanted to simulate how well or evaluate how well the methods or the models will perform. So we have one prediction scenario we call CV1. Is referred to prediction of new lines that were not tested in any of the environments. In this toy example, we have 5 environments, 1, 2, 3, 4, 5, and 5 lines. And the target is to predict line 3 across all of the environments, having information from the other lines in other environments. Here we use a tenfold cross-validation design, meaning we, I think in the morning, Dr. Lipka already explained those concepts. So we split the data, the phenotype, the genotypes in folds. in a way that within the same fold, we will have all of the phenotypic records corresponding to the same genotype. The second cross-validation scheme is in complete field trials, where we have some genotypes tested in some environments but not in others. So here we already have information from this line, for example, observed in other environments, and also we have information from these other lines in this same environment. Again, here we use a tenfold cross-validation, but in this case, we are dividing the phenotypic data in folds. So it might be the case the same genotype will have 2 or 3 phenotypic values within the same fold. So here, very quickly, the results. So one of the first things that we check sometimes is the assumption. So in this case, we have the empirical distribution seems to be close to a normal distribution. And one of the things that I always struggle with, I'm dealing with not dealing, but I talking with other colleagues is many times seems like we are not meeting the normality assumption, but normality assumptions are made on the residual. So its distribution is not normal in this case. After we adjust, we need to evaluate the residuals, and then we can decide from there whether we are meeting or not the normal assumption. So these are just the box plots for environments and lines, as usually happen. As you can see here, most of the variability is explaining by the environmental component. So here we have the environment, the variance components. Sorry, I have to move things around because it's hard to see. So here we have all the different models. As usually happen, always the environmental component captures the largest amount of variability, so 190, almost 200 units at the residual 26, and as we keep increasing or adding more model terms in the models, we were able to reduce to 148, 146 in this case, and we keep reducing the residual values. So, but we are interested in what happened with the environments. So within environments, after we discard the environmental component, we have a very important amount of variability is explained now by the line effect and the main effect of the markers, the weather data, but also the interactions. The interactions keep explaining a very important amount of variability. In this case, we reduce the residual variance with the most elaborate model. So in this case, when we put together the information of the 2 different interactions, we have they explain around 1/4 of the total variability, or 1/6 of the total variability. Okay, now let's talk about the assessment of the prediction accuracy. In this case, for CV1, there's a problem of predicting new lines across environments. Let's say that this second model is going to be the model that will mimic any of the main conventional main effect models. It could be RR block, G block, base A, base B, or any of those elaborate models. We would have expected an average correlation of 0.19. When we include the interaction between each marker and each environment, we boost to 0.29, okay, 0.209. Main effect of the interaction between markers and environmental covariates 0.214, and combining both type of interactions, we boosted until 0.236. So roughly speaking, it's an improvement of around 25–30%. Okay. So the next cross-validation scheme is the prediction of incomplete field trials. In this case, as you can see with the second model, we have a high correlation 0.42, and it's equivalent to the correlation using phenotypic data. So in this scenario, the molecular marker information lose relevance because we already observed the genotype in some of the environments. But still, when we keep adding the interactions with with markers between markers and environments and markers and environmental covariates to keep improving predictability. In this case, around 20%. So another way to evaluate how well we are conducting the predictions is based on the conditional plots, where in the x-axis we have the predicted values or genetic values, in the y-axis we have the adjusted phenotypes. And if we impose a grid selecting, let's say, different quantiles, 20, 50, and 80, or the distribution in both sides, one for the predicted values and one for the observed values, we have if we select the top 20% of the phenotypes, around 60%, 62% of those will have a performance above the mean in fields. And actually around 30% of those will correspond to be among the top 20 fields. This under CV1. Under CV2 is an easier prediction problem. If we select top 20% of the genotypes, we have the around 80% have a performance above the mean, but more specifically around 45% of the top 20 will have a performance in the top 20 in fields. So this model has been applied in other problems, and it can be extended. It's not that it works only with market data, also can consider pedigree data and high throughput phenotypic data. I'm listed here some of the studies where we're using, for example, in Coron, dealing with 582 lines, tested in 9 environments and 78 environmental covariates. This model was able to improve predictability around 166% with CV1 and 150% with CV2. Using combining pedigree and marker, also in maize, this model was able to improve predictability between 50 and 30% for different combinations. And also with soybeans, this model was able to incorporate high throughput phenotypic data to improve predictability between 170% to 210%. So this is what I have so far about the presentation. Now, very quickly, I will move to the practicals. I'm sorry, probably we won't have enough time for answering that many questions, but I think Dr. Lipka shared with you guys the link for a folder which has my name. We have the practicals, and I think also we share the way how we can install DGLR, because this session is pretty much based on DGLR. So I prepared in that shared folder 3 sessions, and I'm gonna talk very quickly, very fast about each one of these different sessions. So the first session it has this structure. It has a folder for data, a folder for where we have the scripts, and a folder for output. So here, I'm going to start with session 1. And here, very quickly, what we are going to do is just to go simulate some data, because I want to show how to expand the metrics of the kinship metrics. So very quickly, here we use OpenR. We create a vector, and actually it's a metric that has 2 columns, a column with yield and the group. So when we type white, we have the yield and the group. So we have 5, 3, 1, 5, 1, 2, 3, 3. So pretty much similar to what we have in the slide. We also create a G matrix. It might not be realistic, but anyway, we are creating a G matrix that represents the genomic data of the kinship metrics for these 3 individuals, how they are genetically related. So we have values 0.5, 0.4, and 0.6 in the diagonal. So now the next step is to create a vector of factors. In this case, so the response is white, is for the first column. A vector with the IDs of the groups, so 1, 2, 3, 3, and a vector, and we create a factor with this. In a way that we are going to expand this factor to be able to include the interaction in this case. Pardon, sorry, to be able to to be able to redistribute these metrics. So we create we use the model metrics instruction to create the incidence metrics where we have again one wherever we have the group that corresponds to the phenotypic value. In this case, we have a diagonal 1, 1, 1, and in the last column we have that one is repeated twice. So here we just have to compute the product between Z, G, C prime, and this is going to return all the expanded metrics. So the metrics that has the genomic data for all of the individuals in this case. So this is the first example. So another example also is here. So sorry, this is what you have to get then when you run the code. Another example has to deal with the construction of the G matrices when we have replicate data now using actual data. So real data from an experiment. And we have that. So the only thing that you have to do in the data on the script that I share with you is you have just to change the path to the directory where the data are stored. So in this case, in my case is UF 2021. And then we read the data this in the data folder. So in the data folder we have all these data. All these objects, white or white2, those are the objects that have the data for the phenotypes. So we assign column 2 to be the column that has information that relates the name of the varieties to the phenotypic data. In this case, we have a data set that has something like 500 records tested in multiple environments. And then we also provide a path to the molecular marker data set. In this case, is X2 CSV. We read the number of fields that we have in this case. We have 114 rows in these methods of molecular markers. And then we start reading one by one each one of the rows in a way that we are going to store this in memory. We did this before because before it was very challenging to deal with large data sets when we have very reduced memory computer. So it's efficient. You can read each one of the rows at a time, and it saves resources. In the next chunk of code, we are doing the imputation, using an imputation. If you remember, some of these markers have missing values. So we just compute the average, the mean across marker positions, and we just assign that as the missing value. And then we compute the G metrics. In this case, use the product between Z, the incidence metric, the X matrix multiplied by itself divided by the number of columns. In this case, the dimension of G is 114 by 114. Okay, so we have the diagonal, different values, etc. So the next step is to expand these metrics to a matrix to be conformable with the phenotypic data. Remember, we have 500 phenotypic records. So for that, we follow the same tricks that we did before in the first practical. So here we assign the row names to be the levels for this factor. We compute the incidence metrics. In this case, the incidence matrix is going to have 500 rows and 114 columns. And it's going to look something like this. Okay. And then we compute the product between Z times G times Z prime. In a way that we are replacing the old G matrix, and the new G matrix is going to have a dimension 500 by 500. And then we save these objects. We also compute the eigenvalue decomposition, and this is going to be helpful to save time when we run the VGLR. Okay, that was the second practical, first part of the second practical. The next part is about running a very simple model where we have used marker data. So this is equivalent to the G-block model, a model that has only G as the covariates that will be used to explain the model. Again, in this case, we load the library VGLR. We read the data. You remember the data has 500 rows, 3 columns. And the third column has information about the yield in this case. So we load what we say before, the result of the eigenvalue decomposition. We create a linear predictor. We start with a list. We call this ETA. And this object is going to have only one model term. So that's why we are assigning the first one. And this is a list where we provide the vectors and the values of the eigenvalue decomposition, and we assume that the model is equal to RKH. When we are providing a covariance structure of the elements to build a covariance structure, and we say that model is equal to RKH, we are pretty much telling the software that we want to run the G-block model. And then we specify a few things. Which column has the phenotypic information? In this case, column number 3. Number of iterations to run. In this case, I'm just using 2,500 because of the time. Number of iterations to discard as a boarding period, 500. And also I set the SIR to be able to reproduce exactly the same results. So I also assign call friend to be the column with the phenotypes. In this case, I said number 3. In a way, the white is going to represent is going to have information for the phenotypes. In this case, I run the model using this VGLR. I provide the vector of phenotypic values and the linear predictor. In this case, a very simple example with main effect of the markers. And I let it run. And it runs very fast. So it finishes already. We save the results. Delete information is not needed. It's about the variance components, or the trace of the variance components. And then we put together the vector of predicted values and observed values in this case, PO. I assign the names and I check the head. So you should have gotten something like this for the predicted values, 91.1283, or you should get something like this. And the correlation between predicted and observed values was around 0.45. So this is an example where I'm running a very simple model without missing values. So just for you to have an idea of how easy it is to run the model using the VGLR implementation. So you should have gotten something like this. finally, we have to run the plots, check plots. We personalize plots, we have labels, etc. And we should have something like this. Okay, this is session number 1. Now, very quickly, I'm going to jump to session number 2. Again, the same structure, we have the data in this case, in this folder, the documents, we have the different things that we're going to use and the output. So here I have a slide. Okay, so in this session, so far we'll check about the GBlob implementation. We also expanded the G metrics. And here we are going to compute some of the models of the model terms, pretty much the covariance structures in this case to fit the model that I presented you before. So you can just follow the slides and try to get an idea of what the flow. Here we have also this doc file where we have the information about how we are computing the different covariance structures. So I already put everything here. Yes. It's a number. So again, I read the content, the data, we check the data file. I assign the column that will have information for the ID of the genotypes. I create sorry, I have the IDs of the genotypes. I create this as a factor. I compute the incidence metrics in this case. Is a matrix of 500 by 144. I compute somehow the evaluate the composition of this, and I save this as model term. So here I'm getting the covariance structure for environments. Also, I'm getting in the next chunk of code the covariance structure for environmental similarities. In this case, I'm loading the data with the weather information. And it looks like this. So we have, I said before, 60 environmental covariates, and we have 139 environments. So I don't know how many we keep for this example, but they match. Okay, they have we have 500 for each environmental covariate. We have 500 values. So here again, we are imputing, because the data is not perfect, imputing and standardizing the weather data. So we go each one of the covariates at a time. If there is a missing value, we just assign the and then we compute a kinship metric, environmental kinship metrics as the product between W and W prime divided by the number of in this case, of environmental covariates. And we save that, and also we conduct the eigenvalue decomposition, and we save. So the next step is, again, as we did before, to compute the kinship metrics based on molecular marker data. So we already did something like this before, so I'm going to just run this code. So we have 2040 molecular markers. So we read, we impute, and we center and standardize. And we compute the G metrics or kinship metrics, in this case, based on molecular marker data. Again, we create the factors, we compute the incidence metrics, and we just expand the G metrics using these incidence metrics, and we save. Again, we compute the eigenvalue decomposition because it makes it easier to run the implementation of the GBlob, and we save this object. So the next step is to compute the interaction between molecular markers and environments and environmental covariates. And this is very easy. We use load the objects that we already saved. So the expanded geometrics and the expanded, or not expanded, but the environmental kinship metrics based on weather data. And we just compute the product cell by cell, in this case, between these two covariance structures. And then we compute the eigenvalue of the composition, and then we save the objects. And finally, we build the linear predictor. So what we are doing here is first we load the VLR package, we load the objects, the Y, it has the phenotypic data, the covariance structure for environments, for molecular markers, for environmental covariates, and interaction between molecular markers and environmental covariates. And here is a place where we build the linear predictor. So we open a list, an object, and in the first place of this list, we are going to add information about the environments. And again, as I said before, we specify the model to be Lipka'sVideo2 in order to have some kind of G-block approach. In the second place of this object of this list, we add the main effect of the markers, again, Lipka'sVideo2. In the third one, we are including the main effect of the environmental covariates. And the fourth one, we are adding the interaction between each molecular marker and each environmental covariate. Here we specify that column number 3 is going to have the information for phenotypic data. Type Y, in this case. We also specify the number of iterations and the burning, so how many iterations we're going to discard. I set the seed to 1, 2, 3, 4, 5 in order it's going to be easy for you guys to reproduce exactly the same results. And then we assign to 5 with the vector that contains the phenotypic data for training the model. And then here we are going to fit this model. A model has information of environments, many of the markers, environmental covariates, and interactions. And we just fit the model. It takes a little longer because it has small model components. And it's all. So we save, we discard the traces of the variance components, and we plot. So this is the scatter plot between predicted and observed values. So it seems like the model did a very good job getting the predictions. In this case, we have a correlation of 0.98, but still we need to compute the correlation within the environment. So we did a very good job of conducting predictions, distinguish between different environments, but still we need to go and compute the correlation within the environment. Okay. So the next step is to get access to different variance components. So we load the object that we use create, and the object is called the object is FM. We save it with a different name, and we can get access, for example, to the mean FM $symbol mu, to the residual variance, to the vector of predicted values, to the number of iterations for burning, observed values, etc. And with each one of the different random effects, we can get the effects. So for the environments, we just have to type FM $symbol ATA1 U. So this is going to be the effect of the environments, the lines, etc. And also we can get access to the variance components. So we can assess from here how important each one of the different model terms was in order to explain the variability. So we have 4 more minutes, and I'm gonna try to hurry in order to be able to be done with it. So we have a third session where we are trying to deal a little bit with cross validation. So you open, in this case, the slide is gonna tell you that we are trying to divide training and testing, and we are going to use data from the training to perform the prediction of the testing. And we compute the correlation between predicted and observed values. And then you can get the codes here in this practical. And also I provided a little more information where you can get a better idea how the pipeline works, because this is just kind of a very small representation. So first we have to set up the work directory. We load the outputs that we have before, the data, of course, the different model terms, environment, weather data, monitor the markers, interactions. We compose the linear predictor similar than before. We have the ATA object, and we were adding one by one each one of the different model terms. We have the specifications, so which column has the phenotypic data, iterations, etc. We set the SIP in order to be able to reproduce exactly the same results. And the important part here is that we are creating this vector Y and A. Here is full of data. It has the responses. But after that, we create a sample, or we sample 50 individuals from 1 to 500 to be part of the training set. In a way that we have in this index the numbers of those selected individuals to be part of the training set. And we assign a missing value to those individuals. In a way that after that, we check again the vector Y and A, and we have 50 missing values across the 500 values. So now the only difference with before is that we add the missing values, but for fitting the model, we have to do exactly the same. We have Y equal to Y and A, and ATA equal to ATA, so the linear predictor. So we run this. Okay. And we save the object. And now the final step is to load the outputs, check I have another script for create the plots. We compute what were the positions of the missing values, in this case, those that we sampled before. We adjust the phenotypic values. As I said before, we have to somehow block the environmental effect. So in a way that we are not predicting these environmental differences. And we do that with this instruction. And the same way, we have just to keep the genetic component in the model. And then we compute the correlation between data and observed values. In this case, it was only 0.19. So as I said before, we were very optimistic, having 0.98. This is the reality. And we compute the plots. So in this case, we have the around 50% of the predicted values have a performance above the mean, but only 20% of the 20% of selected values have a performance on the right quadrant. So in this case, as I said before, this is just a toy example. We are not expecting to have high predictability. The heritability is not high either. But if you are interested in learning more about the pipelines and everything, in the last slide, sorry, in the last practical document I left, I had some links to one of the papers that we just published last year, and we are sharing the information of the whole pipeline there. So you can just click there, and it's gonna take you there. Well, no, that one. Anyway, hopefully it's gonna work for some of you. I don't know why it's not working for me, but I checked this morning. Yeah, you will have all of the information about how to build the pipelines in an easy way, I would say. I'm sharing also this, for some reason it's not working, but we check this morning. But yes, you cannot access, please send me an email and I can provide you a direct access, but it should be easy to access because it's in this paper. So you go and check this paper, you can find the information how to get access to the whole paper. And I think this all I have for now. I'm sorry for having to speak too fast.
Dr. Hakim, thank you. That was awesome. Very, very informative. And well, let's see. I'll be quiet. Does anybody have any questions for Dr. Hakim?
I have a question.
Yes.
Though I've written it in the chat.
Yes.
Oh, okay. I'm just thinking, like, in order to reduce the cost of multi-environmental trials, can we have like few genotypes in different environments and use that to connect and make predictions? And also, can we borrow information from environmental covariables to make GS predictions? Like,
yes, and actually there is a couple of papers that we used published last year and 2 years ago. They are called sparse testing. I add there also sparse testing. And we evaluate those things. And what we found is that it's recommendable to have probably very few genotypes, but those tested in many environments. In a way that at the end, you will be able to observe some of those genotypes or most of the genotypes, not in all of the environments, but at least once. And that will give you a lot of information or flexibility to borrow information across environments. And you can boost the predictability. I think we show easily between 50 to 100% using the interaction models.
yeah, thank you. I'll check it out.
So there is a question here, how to decide the number of iterations. I think one of the things that we have to check are the trace of the variance components. So those values that I was deleting at the end, you remember, corresponds to the trace of the variance component. You can get those in the actually in the output folder. I think it's in this case. So these are those the ETA. So you can go and check a plot of the trace of these things. You can pretty much decide when you see you are reaching convergence. But technically, we don't have to do this all of the time, but we found that probably the model is not that complex. When you have more than 12,000 or around 12,000, it should be more than enough for total number of iterations and 2,000 for modeling. So we have other questions. Should we have determined the most important environmental covariates? We did something like this before, and we were selecting the most important 5, 10, 15. And what we found is that you can increase predictability, but the highest values we're obtaining when we have all of the environmental covariates in the model. So you can learn probably what were the most determinant covariates, but it's difficult to improve the predictability going beyond, I mean, with a very selected, very small set of environmental covariates. I think it's quite similar to what happened before with PPL analysis, where people thought that they would be able to predict easily or to select genotypes based on specific regions in the genome. And they realized that probably adding all of the information together, like genomic selection is a little more powerful. It's kind of the same idea there.
So maybe two more questions and then we could take a break.
Okay, I want to read the last two. If there is a way to explain the reaction norm, the interpretation in quantitative genetics versus the environmental covariates in the concept of genomic selection. Wow, this is a complicated question, I would say, but at the end is, I mean, reaction norm is based on, at least the model we are proposing, the interaction has that flexibility that is giving you somehow the information is constant across the environment, but also like an intercept, but also you have a specific response or slopes for each one of different environments. So it's one way that we are trying to explain how this reaction norm models work versus the environmental covariance. The environmental covariance will give you just without interaction, just an information, sorry, no information, but it's going to explain the performance, but this was a shift in the mix. So we are interested in interactions of both things, how they work together, the intercept and the slope within the environment. The last question is the way to know how to multiple data sets were created, specifically E and W. You mean for this example or in general? If it's in general, you can find some of that information in the manuscript that I share, sorry, the link to the manuscript that I share with you guys. For this, it's a little more complicated because it's data from a private company. So private companies, they won't tell us easily what are those, what are the covariates.
Well, Diego or Dr. Hakeem, I'm going to do an applause on the screen from University of Illinois, and I really enjoyed this presentation, and thank you for making the demo data available. And yeah, I think it is critical that future genomic selection efforts definitely incorporate genotype by environment. And I think that at least I will be following your lead on like the research that has been conducted on those approaches. So thank you so much.
Oh, thank you for accepting me, giving this short presentation. I'm very happy. Thank you so much.
Excellent. Thank you once again. And everybody, I think let's take a break and then let's convene or reconvene in 21 minutes. So that'll be 2:30 p.m. US Central Time. Okay. Okay, so full disclosure, I had to readjust my windows a little bit, so I might be a little lopsided, but I'm going to share my screen. I think we want to go to this desktop over here. Let me see if that works. Okay, so please bear with me while I set this all up and start the presentation, but let's see. Okay, so let me begin this presentation. So, okay, I got, oops, I need to hit share. Oh no, hold on a second. Okay, we're almost there, I promise. Just me dealing with technology. Okay, so we got that. Press share. Okay, so all of you who are looking at this in person, I can see that you can see the appropriate presentation. Those of you on Zoom, can you see my title slide of my presentation? Let's see. And the chat is obfuscated, so let me see. Okay, I see a whole bunch of yeses, so I believe that we are in business. Okay, great. So what we're going to do now is very similar to what Dr. Harkin has done previously, we're going to do a whole bunch, or not a whole bunch, we're going to do 2 demos, okay? We're going to do a GWAS demo, and we're going to do a genomic selection demo, okay? So I have learned from experience and from doing things the wrong way that I don't want us to do the activities in person in real time, okay? So what I'm going to do instead is have slides that talk us through the question we're trying to answer and the output you expect to see. And then I made a note to myself in each of the presentation that says basically, and now Alex is going to run it. So then I will exit my presentation. I will run the demos in real time in R so you can see how it looks like, very similar to what Dr. Hakim has done. And then my expectation is that in about an hour from now, I expect to be finished and with the 3rd of a 4th set of presentations, and we can have another break. Okay, so let's see. Without further ado, let's get started. So, okay, we're in business. So again, I want to say that I really like working with biofortification related traits, in particular tocopherols or tocochromonols and carotenoids, because their genetic architecture is relatively tractable. And so if we run a GWAS, we are likely to find statistically significant associations, and you know, that they make biological sense. And so it's a feel-good set of traits to look at. So tocochromonols, okay, they are lipid-soluble antioxidants, okay, and they consist of 2 classes, tocopherols and tocotrienols, and there's a typo, there should be a T3 over there. I don't know why I didn't catch that until just now. And the one that we care about for biofortification purposes in particular is alpha tocopherol, because it has the greatest amount of vitamin E activity. So yay. Vitamin E, it's an essential nutrient. Suboptimal dietary intake exists for specific population segments, and deficiency is associated with cardiovascular disease and decreased immune function. So in a particular, kernel of maize, we might see this distribution of various tocochromonol compounds in this pie chart. And the one that we're interested in is colored in blue, alpha tocopherol. So as we can see, relatively speaking, alpha tocopherol is not the most frequently occurring compound, right? So what we want to do is boost vitamin E levels by increasing the slice of the pie of alpha tocopherol and hence vitamin E activity, right? So that is the motivation behind this analysis that we've done. So this multifaceted 2-field season grow out, this is the 3rd time we've seen this today. This is the Goodman diversity panel of maize, 281 lines. So then our colleagues at Michigan State measured tocopherol levels or tocochromonol levels for a subset of 252 of these lines. So HPLC was used to quantify our tocochromonol levels, and this is important because these are going to be the Y variables in our GWAS that we conduct, okay? So we fitted a mixed model like we've seen this morning to account for our field seasons and niche phenotype. And then we used BLUPs of our genotype effects, that is our BLUPs of our lines to use as phenotypes for our GWAS model. So in total, we looked at 20 related traits to these, tocochromonols, okay? And we used GAPIT, and we ended up having about just over 294,000 markers dispersed throughout the maize genome. All of these were filtered so that the minor allele frequency was greater than 0.05, okay? So, so we will look at our folder in a second, but here's some information. So for this in-class example, our trait of interest is alpha tocopherol, okay? We looked at a subset of 3,093 markers, okay? Indeed, GAPIT is fast, okay? It can analyze 294,000 markers using the unified mixed linear model. I don't know, I'm gonna make it up. You could probably let GAPIT run overnight for all 20 traits and have results when you get to the lab the next morning. But I don't want to make you sit around for an hour to run all 294,000 or anything like that. So we got a subset of about 3,000, okay, that we'll use here. And we use the unified mixed linear model for each of these 3,093 markers. And we used population parameters previously determined to save computational time. So we have our data set of 4,000 markers with this file name. We have another data set we have another input file that contains our phenotypic data. And then to prevent you from having to navigate through a whole bunch of scripts, I just have a folder that's called scripts necessary for GAPIT. And then I have a master script in the main directory that has everything you need. So I'll say really quickly, this R script over here, okay, it has the some libraries that need to be ran, and we'll take a closer look at it in a second. I also commented out instructions for installing any particular libraries. And one of them is multest, and it's kind of, well, lack of better terminology, weird. But I have instructions on how to get that. So if you don't believe me, this is how the R script looks like when you want to run it. Okay, we'll look at this in greater detail in a second. And here's the second half of the R script. And GAPIT was co-developed by myself and Professor Shiwu Zhang when we were both in the Buckler lab at Cornell. And if you want to look at details on the latest and greatest of GAPIT, please go to Professor Zhang's website, provided over here for the user manual. Now, so let's say that we did what we're about to do in a second, okay? We read in all the data, we ran GAPIT, and we're done, okay? So first thing you want to look at is the QQ plot. Now, how many of you have seen QQ plots before? Rock on. Oh yeah, and a new pass. He's probably sick of seeing QQ plots from me. So here's the dealio with this QQ plot, all right? Now, what is the null hypothesis when you are testing for an association in like a GWAS?
No association?
No association, exactly, okay? So, where should I go? Okay, so what distribution does every single p-value in the entire world follow under the null hypothesis? Oh,
The C division?
nope,
The T?
nope. Okay, so it's not the Z distribution, it's not the T distribution. Anybody participating online want to type a guess into the chat? Oh, 6 new messages. Hey, uh-oh. Okay. Man, sorry, this is Tangent World. This is not making it easy. Let's go here. Okay. Okay, missed my question. Please repeat. Okay, there's one correct answer, but what distribution do p-values follow under every single null hypothesis in the world? Okay, awesome. Okay, I'm getting some correct answers. Okay, under the null hypothesis, every single p-value in the world is going to follow a uniform 0-1 distribution. Okay, translating this into English. Okay, so if the null hypothesis is true, your p-value is equally likely to be any possible value from 0 to 1. Okay, so Now that's the statistical motivation for this QQ plot. The biological motivation, would you believe, if we are conducting a GWAS of 3,000 markers throughout the genome, what do you think is the truth? Like, what's your gut instinct? Do you think the null hypothesis is true for a lot of the markers that we're testing? I would say so. I mean, if I'm running a GWAS, I would expect the vast majority of my markers I'm testing to not be associated with my trait, okay? So let's put these two concepts together, okay? For most of my markers that I'm testing, I'm expecting the null hypothesis to be true, and therefore I would expect most of my p-values to follow a uniform 0-1 distribution, okay? So that is why we're looking at this plot here, okay? Our x-axis is the expected value of our p-value, technically negative log base 10 p-value. Our y-axis is what we are actually observing, our actual distribution of our p-values for our GWAS, okay? So each of these blue dots here represent a p-value, okay? So if most of the dots are lying along this diagonal line, that is suggesting that most of the p-values are most likely being well approximated by the distribution they should be following under the null hypothesis, which is a uniform 0 distribution, okay? So if we see, let me see if I can toggle back to here, okay? If we see like a blue line that goes like this or something, you know that something is messed up with the model that you're fitting, okay? So you know that you're getting an inflation of p-values, and maybe that is indicating that maybe there's unaccounted for subpopulation structure that are inflating the p-values from what we expect to be seen. So what we see here is that everything appears to be fine. Most of our p-values seem to be well approximated by uniform 0 distribution, okay? And then we see 3 dots veering off, okay? Maybe that is, some SNPs that are in the vicinity of true real causal mutations that are resulting in p-values being lowered, okay? So QQ plots are a really useful tool for seeing how much your p-values are being inflated, okay? So any questions here?
What's the name of the distribution again?
What is the name of the distribution? Uniform 0-1. Yeah. So false positives due to population and structure and relatedness does not seem to be an issue for this particular trait. Okay, so here is the Manhattan plot that you'll get, orange and blue Illini colors. So the x-axis here is your chromosome position along 10 chromosomes of maize, and then your y-axis is your negative log base 10 p-value. And I've already heard someone saying it today, but this is a Manhattan plot. Does anybody know why this is called a Manhattan plot? Yeah, skyscrapers, right? So if you have a good Manhattan plot, it'll look like the skyline of like Manhattan, New York City. And then us statistical quantitative geneticists have a very not funny joke, which is if you have a GWAS that is not successful, your Manhattan plot will be a Manhattan, Kansas plot. So looks like we got one skyscraper here, kind of, or I don't know. I've even heard a signal like this being called a helicopter because it's way off and there's no other signals. But anyway, I'll stop joking around with terminology. The bottom line is that we have this peak association over here on chromosome 5, okay? So that's good. And then your output, let's see, we sort the results from GAPIT from smallest p-value, your strongest association, to your weakest association. So we have this peak association on chromosome 5. Okay. So I'll tell you the underlying story of what we found out, okay, from this GWAS, okay, and then I will run the example in real time. Oh, okay, so there's a question, why are we seeing some blue SNPs over here past chromosome 10? So simple. These particular set of markers, there were some markers that were anchored or that were put into multiple positions across the genome, and so they were binned into, I think it was called 9-9 or something like that, but it's an artifact of the marker data. So anyway, if we go back to the original 294,000 markers and look at our trait of interest, alpha tocopherol over here, we have this peak association on chromosome 5. Another peak association we identified for this ratio of tocotrienol traits, we also found something on chromosome 5 as well. So we were able to identify 2 biosynthetic pathway genes in this paper. And so this peak SNP is within this gene, biosynthetic pathway gene. And then this peak SNP was very close to the start of another biosynthetic pathway gene. And here's stuff that's outside of my wheelhouse for knowledge, but we identified this gene and we identified this gene in our GWAS. So yay, we found stuff that makes biological sense. So what this means is that, marker-assisted selections efforts can select on the SNPs that we identified in this GWAS and boost vitamin E and antioxidant levels. Okay, so this morning I was giving a presentation about some stuff we did in soybean, and this is a very similar analysis we've done here, but I do see a question that somebody has typed. So I've seen the same SNPs named scaffolds in soybean SNP data. How do I count for these scaffolds in GWAS? Okay, my honest answer, I don't know that much about scaffolds. And what I would say is, if I'm understanding these scaffolds correctly, which I'm not, it sounds like those are maybe things where their position in the genome is uncertain. So what I would do is, if you're not comfortable with where those SNPs are located in the genome, it does not make sense to analyze them, because you won't be able to measure linkage disequilibrium, and you won't be able to know for sure where are the nearby candidate genes. That's my gut instinct answer off the top of my head. So let's talk about this association for alpha tocopherol, okay, which we identified in our take-home example. Now let's refresh our memories on this plot. Our x-axis is our position on chromosome 5 of maize. This y-axis is our negative log base 10 p-value. And then this y-axis is R square with our peak associated SNP. A lot of information there, right? So these blue and gray lines correspond to our negative log base 10 p-values, right? And the gray ones too, right? So the lines that are blue are statistically significant at 5% false discovery rate. The gray ones are not. This is our peak association over here. And then the purple triangles are R square, a measure of linkage disequilibrium between that SNP in the X coordinate and our peak association SNP over here. So we're seeing, in contrast to soybean, we're seeing a substantial decay in linkage disequilibrium, but nevertheless, over here at 198.5 times 10 to the 6 BP, we see something statistically significant, and we also see something else statistically significant out here. So what we are seeing is short range LD decay with our peak SNP, right? But we're still seeing statistically significant signals up to 4 million base pairs away from our peak association. So what we did was this. We did the same stepwise model selection procedure, okay, that I showed for soybean. And just to drive this home, what we did was we had our unified mixed linear model, essentially. So we had fixed effects to account for population structure, random effects, to account for familial relatedness. So we're filtering out those two sources of false positives. Now, the procedure we did, which is from Segura et al. 2012 multi-locus mixed model, we did a model selection procedure where we considered all SNPs on chromosome 5 for inclusion into the final model, okay? And then the final model that we did for this particular analysis, we ended up having these 1, 2, 3 SNPs all inside of our candidate gene of interest in the final model, okay? And the really cool thing is that we've noticed a 5.76 fold change in alpha kappa levels between the most and least favorable haplotypes. So really big signal. And so what we did was we took these 3 SNPs we identified in our stepwise multi-locus procedure, okay? And we reran our original GWAS with those 3 SNPs included as covariates, and the entire signal disappeared. Similar finding to what we saw in soybean, right? So if you toggle back and forth, we see that all of our signals, including these 2 ones out here, way off in the distance, right? They totally go away, right? So that suggests that these 3 SNPs in this candidate gene, they explain the complex association of signals in these regions. So what I get out of it is that there's really strong evidence that these 3 SNPs are probably in linkage disequilibrium with like a favorable haplotype of this particular gene, and I gotta be honest, I still struggle a little bit when I think in terms of haplotypes. So I also think, maybe there's like several ungenotyped causal mutations that are not in our marker set. And these 3 SNPs, they just form your perfect storm of LD with these 3 calls, with any ungenotyped causal mutations. So I highly advocate such a multi-locus approach. And now Alex will run the in-class demo in real time. Does anybody have a question? Okay, so I have ran this demo before countless of times. I still get nervous that I'm going to mess something up and make a big mistake in front of everybody. So I actually practiced this at least twice before doing this demo. Okay, so when you go to the box folder, okay, and you go to day 2 Lipka workshop, you'll see in-class example. The folder that says tocochromanol GWAS, believe it or not, that is the GWAS take-home demo. Okay, so I described all of these files in the slide. Okay, so what you want to do is you want to go to the R script, which is over here. Okay, so here are all of the packages that need to be installed. Multitest is an awesome package. It's part of Bioconductor, and I know this is kind of the hoop I jumped through to install that. But anyway, but there's probably a better way that I'm not doing. So first, let's read in the prerequisite files. Oh yeah, and you all can see my screen, right? Groovy. All right. So I'm going to set my working directory. And then this is just a housekeeping trick to keep my working directory straight. So now I'm going to jump into this file over this folder over here to read in this code. Oh yeah. Oh, there's something I want to say that I didn't say. When I developed this script like a couple of years ago, my intention was to, you know, once you have all of the R packages downloaded and installed in your local workspace, I wanted this to be able to run on a laptop with no internet connection and only 4 gigs of RAM to run stuff. So I really tried hard to streamline stuff as much as possible. For me, a person who does not have a master's degree in computer science. So anyway, that spiel is over. So this is just to help gap it. Line 26 is just to point gap it to where all the data are kept. So this is the phenotype file that you read in. So if we go really quickly, view my Y. So our rows are individuals, are our genotypes. And then this is the genotype ID. And then this is the trait value. Okay. So, okay, this line, dir create, this is the coolest thing in the world. Check this out. So here we are. This is our directory right now. So when I create that, bam, check this out. We now have a folder called results. So all of our results are going to be put into there. And now, now we just run gap it. So let's see. Okay. So back in the day, before gap it, I understand that it took a much longer time to do a GWAS. And so one of my colleagues used to have a slide with just like a picture of coffee, because it said, go have a cup of coffee while the GWAS is being ran. But now, thanks to stuff like this, we can speed that up. Yeah, so while we're waiting for the kinship matrix to be calculated, does anybody have a question? Sorry. Oh, so the line that says model selection is equal to true. So this over here. Okay, so what this is this. So the question was, what is line 72 that I'm highlighting right now? So this is BIC based model selection. Okay, so short version is it does backwards elimination for your principal components that are in the model. Okay, longer winded version is this. Different traits are correlated with population structures to different degrees, right? So if you have a trait that's not highly correlated with population structure, those principal components in the model, they're just taking up space and taking up degrees of freedom for your test, right? And so this model selection thing, what it's doing is it's essentially, you know, taking out your principal components if you really don't need them. Great question. And I remember there's one weekend back in summer 2011 where I wrote the BIC model selection, and it was a lot of fun. So here's our folder that says results. Okay. And gosh, see, these are brand new. I hope this worked. Let's see, are we in business? Okay, yes. So I got the PDF and it went and it jumped to a different window. So let me see if I can move it over here really quickly. Okay, good. It still works. Okay, good. So that's just an example, like we are able to run the demo in real time. Oh, that's something else. Okay. Okay, so great. So that is running this demo in real time. Does anybody? Oh. Okay, there is a question online that says, can you please, actually, I see two questions I'll answer really quickly, and then I'll move on back to the genomic selection. Okay, so, okay. It seems GAPIT is really suitable for polyploids. Yeah, so the question is, should you run GAPIT on polyploids? Short answer is there's a GWAS poly from University of Wisconsin that was specifically designed for polyploids. And if I remember correctly, the most important thing that it does is it takes a dosage of heterozygotes into account. Because if you have an autopolyploid species, you could have many more copies of your allele at one particular locus. GAPIT does not account for that. GWAS poly does. Now, if you just love GAPIT and want to use it, if you have either an allopolyploid species where you got that behaves like a diploid genome, or if you have an autopolyploid that segregates very similar to a diploid species, maybe you could wave your hand and use GAPIT, but I would probably still use a GWAS package that's specifically designed for polyploid species. Okay, so with interest in time, why don't I go, if I can get there, here we go. Let's move on and talk about what's it called? The rest of the demo. And I lost my presentation. Where did it go? Okay. Okay. Did I delete did I close I might have closed the presentation. I'm sorry, everybody. So let's go here. Okay. So we are 2:30 to 3:30 and okay. Oh, let's see. Where did my presentation go? Okay. Okay, hold on 1 second. This is interesting. Okay, so I'm going to close PowerPoint and reopen it. Interesting. Why can't I see that? Oh. Save. Okay, so let me reopen this. Okay. And it's opening, hopefully. Okay. Ah, so close. And then we got this one. Yay, okay, phew. I was afraid that I was going to lose the entire presentation in the middle of this workshop while over 100 people were watching. And we're back in business. How embarrassing that would have been. Okay. So here's the in-class example of genomic selection, okay? We're going to use this versatile data set, this 281 member diversity panel. And it was grown at Purdue for 2 field seasons. And so we quantified carotenoids for 252 lions. And like I said already, we have, there is a near Mendelian association between the PSY1 gene in the carotenoid pathway and yellow versus white kernels. And so therefore we only analyze a subset of 201 lines that range from light yellow to dark orange kernel color. So for the in-class example, okay, we look at a ratio of compounds, okay? So we look at the ratio of these two compounds over here in the numerator, and then we look at this compound plus this compound in the denominator. Okay. And oh man, I was about, okay, quick tangent. We would expect to see this gene Y key on chromosome 8, but that's irrelevant to here because this is genomic selection. So we had 284,000 markers, a slightly smaller number because we filtered on monomolar frequency of 0.05 for the smaller sample size. And our statistical model is the RR blood model. So here are the scripts that we need to read in, okay? And so we have this R data file that I'll talk about in a second, okay? And then I have a folder called scripts to read in, and then I have a master R script, okay? So here's how the R script looks like before reading it in. And then here's the bottom half. Okay, so now let's start talking about what's happening here. So we have this data set, you know, this ratio of carotenoid compounds, right? And so what we did was we conducted five-fold cross-validation, okay? So at each fold, at each fifth, approximately fifth of the data set, we would, you know, use the remaining 4/5 to train our blood model and then calculate the prediction between the observed and predicted breeding values of this trait across our 5 folds. So here are the particular correlations we got when each of these subsets were used as the training set. This is the average, the mean correlation, and then this is the standard deviation. And why did I put this here? I don't know. I thought it might be useful in the future for analyses. So the prediction accuracy is 0.35. So that's my interpretation. So this means that across 5 folds, the average Pearson correlation between observed and predicted trait is 0.35. Anybody have any questions? Okay. So here is a plot that Dr. Harkin has shown in his presentation a little while ago, and I'd like to elaborate on it because it's really important. Okay, so, okay, here I'm going to ask for a little bit of in-class participation. Can somebody just speak out and tell me what trait they are interested in and what the units of measurements are? Flowering time? Okay, and what's the unit of measurement there? Days? Okay, perfect. And that would be sorghum, I'm guessing? Millet. Oh my gosh, that is awesome. Millet. Okay, sweet. So flowering time in days, okay? So let's say, you know, consider this hypothetical scenario. We have a really accurate genomic selection model, okay? It does a good job of, you know, pointing out the top performing individual that gives the best flowering time, okay? But then let's say that predicted GEBV for that particular line, which it correctly selected, let's say that the flowering time was something ridiculous, like 2,000 days or something like that. I mean, I am guessing that that would be a ridiculous value, right? Okay, so what this plot is doing is it's telling us how ridiculous our estimated breeding values are from our statistical model, or not ridiculous, okay? And putting it into kind of lesser silly terminology, and actually using terminology that I no longer agree with, we're looking at our bias of our predictions, our bias, our BIAS, okay? So a good genomic selection model should be able to predict genomic estimated breeding values that are in reasonable units of measurement and in reasonable range of values. Okay, so this XY graph, really what it is, it's a quality control check. Okay, so our x-axis is our predicted genomic estimated breeding values, and then our y-axis is our observed values. Okay, and then this line over here is a simple linear regression line that is fitted to these data. Okay, if your model is not biased, i.e., if it is not giving unreasonable values of your estimate and your slope, okay, if it is not giving unreasonable values, your intercept estimate should be around 0 and your slope estimate should be around 1. Okay, so here we see that the intercept value is 0.89, so that's a little bit away from 0, right? And then the slope is going to be is a 0.9, which is kind of close to 1.0. Okay, so my interpretation of this is that maybe there's a little bit of bias present in the data. Okay. Okay, so any questions on this particular plot here? Okay, and now I'm going to run this demo in real time. Okay, so let me X this out, and hopefully I will not lose that presentation again. So let me start from a clean slate. So I'm going to do remove list is equal to ls. So now I removed every single file that was in the R workspace. And just to, okay, and I cleared my console. So we're literally starting from scratch. So here is the folder with your carotenoid, the genomic selection. Okay, so first thing we're going to do is we're going to set our working directory. Okay, and we're going to use the RR package, the RR blood package, another package from Professor Endelman, to do this genomic selection. I'm going to use these other two plots. Now, here is a clever thing that, or maybe not so clever thing that I do. So instead of reading in text files or CSV files of, genotype and phenotype data that might take a long time, instead what you can do is read in those files like the first time you plan to analyze a data set, and then you can save your R workspace, okay? So you don't have to read in those files again. So that's precisely what this R data file is. That is an old workspace from when I originally read in the files. And if you use the, I'll just type it down, save.image, and then blah.r data. I'm not actually going to run that line. That's how you can save your files in a quick and efficient manner. Okay, so let's see. Here are the files. Here are the scripts that I read in to do this. So I basically took the RR package and I wrote a silly little function that will do k-fold cross-validation using RR models. And then I also use gapit because I can do some, changing with the format of the files so they can be read into RR. But anyway, we now have those files read in. So here's our genotype data, okay? These data are in a HapMap format. So our rows are going to be our different SNPs. And then our column, so here's some information that is, well, lack of better terms, irrelevant for the genomic selection. But then starting on column 12, we start to have our different individuals. So 3811 is the first individual of this diversity panel. Okay, so let's see, dimension of my G. I just want to see what the rows and columns are. So we got 462,703 markers and 212 so 200 individuals, okay? And then our phenotype data is going to be in the same format as the phenotype file that we had for the GWAS example. So our rows are the individuals, and then this is the, the name of the lines, and then our trait of interest. Okay, so we had 201 individuals there. Okay, good. So this line over here on line 27, okay. I'm going to be honest with you, okay? So running genomic selection on, 462,000 markers, and then we filter by minor allele frequency, that is going to take a long, it is going to be longer than like maybe like an hour or something like that. So it would be really boring if you watch me run this, okay? Also, remember, what I wanted to do is have this being able to be ran on a computer with 4 gigs of RAM or less, or maximum, okay? So what I did just for demonstration purposes was I'm only going to look at the first 1,000 markers, okay? So those results that I showed on the presentation are just using the first 1,000 markers, okay? So another thing that Professor Harkin showed that I want to re-emphasize is a seed number. Now, how many of you are familiar with setting seed numbers? Okay, some are not. That is cool. So the beauty of a seed number is that if you know what your seed number is, you'll be able to replicate the results of your study, okay? So when we're doing 5-fold cross-validation, we are randomly partitioning our individuals into our 5 different subsets, right? So if we know what the seed is, we'll be able to repeat that exact same randomization into our folds. So what I usually do is I have a value where I randomly select a number from 1 million, from -1 million to +1 million, and I record that seed number. Okay, so when I first wrote this example, I ran line 30 and I got this particular number for the seed number. So I'm going to set the seed number to this, okay, and I'll prove that I did it. Bam. Okay, so I will now be able to replicate my results, hopefully. So I'm going to create a directory that says results genome-wide. And now I'm just going to let it go. I'm going to perform this 5-fold cross-validation, and it's done already. So here is the output that we just created. So let's see, we got, oh man, it opened it up on a different window. Hold on. Okay. Okay, so here are the results from our 5-fold cross-validation. I outputted it as a text file. I know, not really fancy, but here's our prediction accuracy. So I know from experience that this is going to be the mean prediction accuracy across the 5 folds, 0.35. And then, awesome. Okay. And then here is the file that we can look at to assess the bias. So our y-axis is our observed trait values, and then our x-axis is our predicted genomic estimated breeding value. So there, it does look like that there might be a little bit of a bias because the intercept is 0.89, which is far away from 0. Okay, so, but also remember that to save computational time and to save computational expense, we only ran this on the first 1,000 markers. If you were to run this on the genome-wide set of markers, I hope that there will be less bias in these prediction accuracies. Okay? Yes.
This script, maybe I missed it, but did we assess training set of this script?
Okay, so the question is, with this script, do we assess a training set? Okay, so for this particular data set, no, there's not a separate a priori training set. Yeah, and you know, that is actually, I mean, that is a fantastic question. So this particular script that I'm sharing, this is assuming that what you have in hand is just one data set. And basically, we're going to do the k-fold cross-validation procedure on that one data set in hand so that we can evaluate our prediction accuracy on only that data set. Great question. Are there more questions? Let's see, I should go to the chat.
That's what this is. This is just looking at what came out of your training set that you put out of your actual data, and you made predictions with that data set itself, and then you plotted them on this.
Yes, yes. And so let me elaborate on Adam's question. Okay, so each dot in this XY graph, that is one of the 201 individuals that we measured our traits on. Okay, so the way that you obtain your XY coordinate for each dot is your x-axis, sorry, let's start with our y-axis. So the y coordinate of each dot is the actual observed trait value. The x value is going to be the predicted genomic estimated breeding value of that individual done within the context of 5-fold cross-validation. That is a really great question. Okay, so I see a question on the chat. Okay, what is the predicted data set? So that is going to be the fifth fold, the fifth subdivision, you know, of your 5-fold cross-validation. And it changes for each validation set. And I don't like the way I said that, so I'm going to answer the next question and I'm going to see if I can elaborate on that. Which parameter were you using when transformed to normalize to phenotypic? If it was log transformed, Box-Cox, or any other method? Okay, so we use the Box-Cox procedure on this. And if you want to look at this in greater detail, I'd be happy to share the paper that we published in Genetics on it. In some instances, we see negative prediction accuracies. What could be the explanation for this? Right, so sometimes you see negative correlations for prediction accuracies. And let me tell you, when I first saw that, I thought that I royally messed something up, okay? But no, it is understandable to get negative prediction accuracies. And what it means is that your genomic selection model is not doing a good job of estimating predicting genomic estimated breeding values. So that means that either you're not using the right training set, you're not using the right model. And I don't want to say give up, don't do genomic selection, but yeah, it just means that you need to change something in order for genomic selection to work. Okay, Alexander, please share us the transformation details. Okay. Let's see. Yeah. So if you'd like to follow up with me, Sergey.edby, I'd be happy to give you, I'd be happy to share our paper we published on that. Now, let me see. Let me make one more attempt to answer what is the predicted data set, and I'll try to be as concise as possible. When you're doing k-fold cross-validation, so you fit your genomic selection model in your training set, which is your, k minus one of the folds is used to fit that data. Then the individuals and the kth fold is used to predict. So that kth fold that is not included among your data set to fit your genomic selection model, that is your predicted data set for this example. Okay, so is this related? Okay, great. Okay, so okay. Does anybody, y'all attending in person, have any questions? Yeah, I can go back to the code. Let's see if I can get my mouse to go there. Sure. Yep, here's the code.
So if you were going to use a separate training population instead of using the cross-validation, at what point would you input that? Where?
Yeah, that is a good question. What I would do, honestly, is let's assume for a second that we want to use the RR blood package, okay? I would go into the RR blood manual and follow their example of how to do it. But basically what it's going to look like once all the dust settles is you're going to have a training set, and then you use an RR blood model to fit your individuals in there. And then you will have another data set where you plug in your values and use it to predict, okay? And I think one slight tweak to that, and I'm just speaking from memory, is you might want to technically have your phenotypic values of your training set to NA, and then you can just join up, you can like R-bind or combine your genotypic data and your phenotypic data from your both training and validation set. And by setting your Y's to NA, you will essentially be masking the phenotypic values of your validation sets. Great, so it is 3:30 p.m. Central Time, so we can take a quick break. And I heard somebody with their microphone that was not off, so maybe they have a question. And I basically, let's take a 29-minute break. I will be back for the last bit. And I'll be happy to answer questions in the meantime. Zoom recording. Okay, good. So those of you who are listening to this on replay, you didn't have to listen to my rant about making sure you don't see my inbox. Okay, so play from current slide. We're good, we're good, we're good. Okay, should I use genomic selection, marker-assisted selection, or both? Okay, so I'm going to begin this last lecture, if you will, with the take-home messages, okay? It depends, okay, on the trait that you're looking at, on whether you should use marker-assisted selection or genomic selection or a combination of both. There is no guaranteed thing that's optimal, but a safe bet is to use genomic selection, is my opinion. So I'm going to show an example of marker-assisted selection working as equally as well as genomic selection for a polygenic set of traits. My favorite is carotenoid levels in maize grain. I'm going to show another example where genomic selection can outperform marker-assisted selection. And I'm going to look at fusarium head blights in wheat. And then there is going to be time left. I'm going to show an example. Actually, it is Dr. Brian Rice's master's thesis showing that combining marker-assisted selection and genomic selection is not guaranteed to be optimal. And that's me being nice, okay? So this is a simulation study conducted in maize and sorghum, okay? So let's go over the good old data set we've been looking at. We got a 281 member Goodman diversity panel grown at Purdue, 2009, 2010. I forgot to say it, so I'll say it. It's maize. And then we looked at carotenoids, and we looked at a subset of 201 lines where the range of kernel color is from light yellow to dark orange. So this is a complicated graph at first, but what it's going to show us is that carotenoids are controlled by a relatively small number of QTLs. So what we did here is we looked at the maize nested association mapping panel, okay? And we've performed basically a QTL analysis, I did not pronounce that. And so our x-axis is going to be the number of QTLs identified per trait, and then our y-axis is the number of traits. So, for example, let's go to this x coordinate of 9. We see that there are 2 traits where 9 QTL are identified. Then over here, I see this 21. So there's 1 trait where 21 QTL are identified, okay? So our carotenoid traits are colored in yellowish orangish, and then our tocochromanol traits are colored in blue. So would you all agree with me that the orangish yellowish bars are closer to 0 than the distribution of tocochromanol traits? So that is showing evidence that carotenoids seem to be controlled by a relatively small number of QTL, okay? So we can take, what we can take home from this is that carotenoids seems to be a bona fide oligogenic or simpler trait, okay? So the question I'm going to ask is it really necessary to use a genome-wide set of markers if, you know, these carotenoid traits are controlled by a smaller number of genes? So what we did was we compared our prediction accuracies using genome-wide set of markers, SNPs that are in the vicinity of 58 a priori candidate genes, okay? And we already looked at these in the pathway level analysis, and then a really laser focused subset of SNPs in the vicinity of 8 a priori QTL identified in prior studies. So here is a description of the 58 a priori candidate genes. So we looked at all genes in the carotenoid biosynthetic pathway, as well as related pathways, the so-called degradation pathway, and I guess this is called a precursor pathway. Oh, I was close. I guessed it was about 8,000. So 7,408 SNPs and 7 indels in the vicinity of these genes were considered. And so we would run a genomic selection model, but we would only train it on these 7,408 SNPs. Okay, makes sense? Okay, and we would also consider 8 priori QTL. So the genes producing these enzymes that are circled, we only considered markers that are in the vicinity of these genes, which amount to 944 SNPs and 7 indels. Okay. So here is a picture of the results. Okay. And so what we did here was, five-fold cross-validation. Okay. So the x-axis on each of these bar charts are the particular traits that we looked at. The y-axis is our prediction accuracy from five-fold cross-validation, okay? And then this over here is using only those 944 markers in the vicinity of the 8 candidate genes. And then here is a larger subset of 7,448 markers in the vicinity of 58 candidate genes. And then here are the results for genome-wide set of markers, right? So what do you all see here? Do you want to comment on what you're observing? Yeah.
Seems like genome-wide.
That's what me and my colleagues observed with these results. So looks like genome-wide prediction, if you look at the heights of the prediction accuracies, they look very similar to the pathway level and the carotenoid level, right? So we compared these 3 respective subsets of genome-wide markers, and we're seeing relatively similar prediction accuracies. Do you all concur with that inference? Yeah, so what we concluded was that models with markers near these 8 QTL were as effective as a genome-wide set of markers. So if we had a limited set of resources and we, did not have, the resources to obtain a genome-wide set of markers, looks like for these carotenoid traits presented here, we can get away with just using markers in the vicinity of these 8 QTL, and we should get accurate predictions. Okay, so do we need a genome-wide set of markers for these carotenoid traits? It does not appear so. And if I might be a little bolder, I'll say no. Okay. Any questions? And on the comment box, yeah, I will send an update on the Zoom link for tomorrow's workshop. And once we wrap up this lecture. So now we're going to see a completely different set of results, okay? And Anoop, I don't mean to pick on you, but these are some data in wheat that I analyzed back in 2016. And so what I'm about to do is probably say a lot of stuff that are incorrect about wheat. So please call me out when I say things incorrect. But I contributed to this analysis for the genomic selection. So this is Fusarium head blight in wheat. It causes significant grain yield, and it's thought resistance to FHB is thought to be a complex trait where you have one major large effect QTL followed by a whole bunch of smaller effect QTLs, okay? So what was done was this. We had that there was a breed, 273 breeding lines, okay? And then resistance to FHB was collected from 3 different field seasons, and we had 19,992 SNPs. And so we wanted to ask a very similar question to what we asked in the carotenoid result stuff in maize. Is a genome-wide marker set necessary to accurately predict this trait? So we compared prediction accuracies using marker-assisted selection genomic selection, and then GS with markers from marker-assisted selection as fixed effects. And the rationale being that if we included those markers from marker-assisted selection, maybe they could boost the prediction accuracy because you're more accurately accounting for that large effect gene. Okay. So here, 4-fold cross-validation was conducted. So the results were that our genomic selection models consistently outperformed the marker-assisted selection models, okay? And our genomic selection models with markers as fixed effect had the highest prediction accuracies. So here we're seeing a totally different result from the carotenoid results, because remember, for the carotenoids, we saw that we saw similar prediction accuracies whether we use a genome-wide marker set or there's 2 subsets of markers, right? Here we're seeing the opposite. GS is always the best, okay? And even better, GS with marker-assisted selection had the highest prediction accuracies. So any questions there? So have you ever heard of the inside trading effect with respect to genomic selection? Well, here, I'm going to tell you what it is. But so when we do k-fold cross-validation, why do you think we fit our genomic selection model on specifically the individuals from the training set and not the validation set? Or here, let me put it this way, okay? What do you think would be the not so good implications of using the same data set to fit your genomic selection model and to make predictions? It would what to the prediction accuracy? Yeah. You'd be overestimating, you'd be overfitting. Yeah, you would be seeing higher prediction accuracies than you might expect. What do you think would happen with the prediction accuracies if you were to take that genomic selection model and try to make predictions in another data set? Right. It would be much lower. So, okay, you all got the concept, okay, but I will elaborate this on a little bit further, okay? When you have your training data set, you have that perfect storm of LD between genotyped markers and ungenotyped causal mutations, right? That exact combination of LD is not going to exist anywhere else in any other data set in that particular form, okay? So when you fit a model in your in a training set and you make predictions in that same data set, I would expect the prediction accuracies to be higher than what I would see in other data sets because we are capturing that LD structure perfectly, okay? And so let's expand upon this ever so slightly, okay? Now let's say that I'm looking at a particular marker that is maybe a peak association from GWAS, okay? First of all, I would not expect that marker to be causal, okay? I talked to a colleague of mine and I really respect their opinion, and they said that maybe 20% of markers in a genotypic data set are actually causal. And I don't know where they came up with that 20%. But anyway, so that marker, its LD with causal mutations, is not going to be exactly the same in your prediction set. So maybe maybe that prediction set has that same causal mutation segregating, but maybe there's some other marker that is better, right? So what this paper looked at explicitly was such inside trading effect, okay? So you're boosting prediction accuracies by using, here, I'm gonna steal my own thunder. So if we take a QTL that were identified in this data set we analyzed, and the same QTL were used to assess prediction accuracy, our prediction accuracies are going to be unfairly inflated and inaccurately inflated. So we indeed showed in this paper that this insider trading effect was a real thing, and you got to look out for it. Okay, so let's go over the take-home message, and then I'll see if there are any questions. So the take-home messages are this. For a complex trait, genomic selection, or sorry, for this particular trait, FHB resistance, genomic selection outperformed marker-assisted selection. And whenever peak-associated markers are used to predict traits in the same data set, you should expect to observe inflated prediction accuracies. Okay? Okay, so are there any questions? Adam.
Got a more broad question.
Mhm.
So if you were talking about marker assisted selection, you have your GWAS, you identified a SNP that's in theory linked to a major QTL. How do you actually move that into forming your marker? You know, are you going to always have to be genotyping it, or can you just create a PCR marker to look for your SNP?
Right. So if we conduct a GWAS and we identify a peak marker, how would you incorporate it into marker-assisted selection? Okay. I'm going to give a statistician's answer, and please ask this question to Dr. Arbeles tomorrow when he presents, because he'll be more qualified than me to answer this. What I would do, you know, oh my gosh, let's say that I've done a GWAS, and let's say I used a bunch of GBS markers, okay? Then what I would do is in an independent set of breeding material, I would sequence that you know, breeding material with the same GBS markers, and then make marker-assisted selection on that particular GBS marker. Yeah. Oh gosh, that was a simpler answer than I thought I was going to give, but does that make sense? Okay, and we can ask the expert tomorrow and see what he thinks. Are there any other questions? Yeah.
I guess how are you actually simulating the marker assisted selection? So was that simulated?
Okay.
in the two?
So the question was, in this example, was it simulated? No, it was not. So what was done was, what did I say, 271, 371 wheat inbreds. So what was done was that a GWAS was conducted across the whole 371 inbreds, okay? So, you know, you had that unfair boost in prediction accuracy because, you know, that same data set was used to conduct the GWAS, okay? In this next example I'm going to give in a second, what Dr. Rice did was run the GWAS separately in each training set to make sure that there's no insider trading effect. Okay. Any other questions? Okay. Okay, so let's see. Okay, I got 3 questions that I'll tackle, that I'll answer really quickly. Does it mean we should not use SNPs associated with the traits? No, I think you can use SNPs associated with the traits, but just make sure you're not using the same data set for marker-assisted selection that you are for your GWAS. What about enlarging the training population with working germplasm available in a breeding program? I think you can do that, but you would again want to make sure that you separate out your, say, GWAS into a training set so that you use your peak associated markers in an independent set of data. So is it not advised to use GWAS peak markers for prediction? Okay, so that last comment, I would say it's not advised to use peak GWAS markers for prediction in the same data set you conducted the GWAS in. I suggest doing it on an independent set of germplasm that was not used to conduct the GWAS. Do I agree with that? Yeah, that's my working answer. I'm going to stick to it. Are there any other questions? Okay, so here is a recap of the RR blood model, okay? And we're going to go over the bells and whistles, and then we're going to talk about what it has to do with what we're talking about. So our Y variable is our phenotype of interest. And so if we have a set of P markers, each of them are included in the model. And then its additive effect is included as a random effect. And then we have our error term, and we have our intercept, right? And then the BLUPs of the predicted marker effect are subjected to this ridge penalty. So a thing to point out is that all predicted marker values are equally penalized so that they are shrunk to 0, okay? So what this means is that, let's say that we have 1 or 2 markers that are tagging a very large effect gene. You know, they might be unfairly underestimating the effect of this large effect gene, right? So, and I just stole Brian's thunder. So here's a picture of Dr. Rice back when he was a master's student. So let's suppose we had a complex trait with several large effects. Is this penalty, is this thing that I just said in the previous slide, are we substantially underestimating or underpredicting these large effect genes? So random effect markers that have this ridge penalty applied to their predictions, you know, they have that penalty, but fixed effect markers included in the model do not. So Brian's hypothesis was that GS models can make more accurate predictions if they account for large effect genes, okay? That was our working hypothesis. So the research question was, if we go ahead and augment the standard RR blood model with peak GWAS markers that tag these large effect genes, can we increase the overall prediction accuracy? So we did a comparison of a traditional RR blood model versus an RR blood model with fixed marker effect covariates. And again, we would run a GWAS in the training population and include the peak associated markers as fixed effects. And we did this across a wide range of genetic architectures. Okay. Okay, sorry, I see a really quick question. Let me see if I can tackle it. I think I missed this, but if the training set is a subset of the same experiment, or is it made of individuals in the next generation? Oh, I see. I'm not, so that is a good question, Alejandra. I'm thinking about things in terms of just a single generation. Okay, so you have, so the bottom line is that the training set is separate from the validation set. So the GWAS is ran in the training set, marker system selection is run on the validation set. And I'll be happy to elaborate on that in a little while when there's questions at the end. Okay, so we conducted a simulation study where we had the same good old maize diversity panel and genotypic data from there. And then our sorghum diversity panel from the, which I think is from Morris et al. 2013. And so we randomly selected markers to be quantitative trait nucleotides, okay? And we simulated traits in 2 configurations, okay? One was your standard complex trait where your effect sizes of your QTMs get sequentially smaller, smaller, and smaller. And then the so-called type 2 traits, which we made up for this paper, terminology that is, we had one really large effect QTN, and then the remaining QTL effects all had smaller effects. And then we had a user inputted heritability. Okay, so across these two configurations of traits and two species, we did a 5-fold cross-validation study. So we would run the GWAS in the training set, okay? And then we would evaluate the prediction accuracy of an R-BLET model plus a peak-associated GWAS SNP in the validation set. And we did this for each possible simulation setting and species, okay? We would repeat this 50 times. And okay, Anoop knows this. One thing I love doing in my class is a show of hands. How many of you think that including these peak-associated SNPs will increase prediction accuracy more often than not? Okay. Okay. How many people think no, it will not increase prediction accuracy? Okay, good. Okay. I thought coming into this study, I would overwhelmingly see a boost of prediction accuracy whenever you include those peak associated markers. Let me show you how wrong I was. So actually, when Dr. Rice first ran this experiment, the results were so bad that I thought that there was an error somewhere. So let me show you how horribly this idea of including fixed effect covariates can possibly be. Okay, the first row is our results for simulating traits in maize. Our second row is results for simulating in sorghum. Our first column is where we have a standard complex trait. And this column is where we had a standard complex trait with a large effect gene, a large effect QTN included. Our x-axis on each of the graphs are number of peak-associated GWAS markers we use as fixed effect covariates. And then our y-axis was the mean increase over a standard R or BLET model, okay? So I know that the numbers on the x and y axes are really small, so let me add this visual aid. This is a y coordinate of 0. So do you see how most of the box plots and most of the dots are below 0? That means that more often than not, overwhelmingly more often than not, we are observing a decrease in prediction accuracy, an alarming decrease in prediction accuracy when we include peak associated GWAS markers as fixed effect covariates. Okay, so this approach of including fixed effect covariates tagging large genes, they should not be blindly used. Okay, it might actually do more worse than good. Okay, but it gets even better. Okay, so you can also increase your variability in prediction accuracy, okay? So here's a snapshot of one set of results. Our x-axis is number of fixed effect covariates, and then our y-axis is our prediction accuracy across 50 replicates, okay? So here is the standard R or BLET model, okay? Now, do you see how smushed up this box plot is relative to the other number of fixed effect covariates? So there is a substantial noticeable increase in variability of prediction accuracy. So not only does it have a potential to decrease your prediction accuracy, it can also substantially increase uncertainty in your prediction accuracies. Okay. So I know I just showed you strike 1 and now I'm showing you strike 2. Let me show you strike 3. So remember when we were looking at that XY graph of like observed phenotypic values plotted against predicted genomic estimated breeding values, and we were fitting that simple linear regression model. And so if your slope was around 1, your slope estimate, and your intercept estimate was around 0, you would conclude that there's not a lot of bias. Well, let's take this example for this one particular trait, okay? So what we have here on our first row, this is your standard R or BLET model. So this is the intercept estimate, and then in parentheses, we have the standard error, okay? And then here's our slope estimate and standard error, okay? So sure, this intercept estimate is far away from 0, but the slope estimate is close to 1, which is what we would hope it would be if you have unbiased, right? So when we add one fixed effect covariate, bam, look at this. The slope estimate jumps up to 1.69. So way out of the ballpark of a desired slope estimate of 1, right? And then when you continually add fixed effect covariates, it then goes back down to 0.98, but you can also increase the bias of your predictions. So if you want to use genomic prediction, okay, the risks of including fixed effect covariates might outweigh the benefits, okay? So what should you do? Well, hey, I just gave you all an R script that does k-fold cross-validation. So tweak that script, conduct a cross-validation study to see if you are actually observing an increase or a decrease in including fixed effect covariates in your model. If you're not, no harm, no foul, okay? You'll just go ahead and use the R above GS model that yields the highest prediction accuracies in your pilot cross-validation study, okay? So that concludes this presentation. So I'll be happy to answer any more questions anybody might have. Yeah. Yeah, so why do I think it lowers the prediction accuracy? Yeah, so let's look at this graph over here. Yeah, so the factors that might be responsible for lowering prediction accuracy, I think first of all, it's LD, linkage disequilibrium, between our peak associated GWAS marker and our causal mutation, okay? I think that's one factor. So differential LD between training and validation set. And then another factor, I think it's a small sample size, because our sample sizes are 281 for maize and 320 for sorghum. So actually, I presented this at a conference at least once, and I was talking with an animal quantitative geneticist. And what they were telling me is they think that once your sample size goes to infinity, you would not see a result like this for like a much larger sample size. Like you would probably see that including fixed effect covariance would be better. But there's only one way to find out, right? So I would definitely be interested in doing this study in like, I don't know, like a 20,000 head dairy cattle or I don't know, something like that, and see what happens. But those are my speculations off the top of my head. And I would say that Brian and I had a lot of thoughts that we incorporated into the discussion of this paper. So definitely check it out, and definitely ask Brian once you get back to Colorado. Oh, I see some questions. Okay, so this says, so BGLR model works well in this case, right? Because we can fit as prior the fixed effect using generalized additive Bayesian model. Okay, so let's dissect that question. And heads up, my answer to that question is going to be I don't know in a very elaborate way. Okay. So BGLR model. So BGLR is that R package that Dr. Harkin has shared with us. And that is a suite of Bayesian genomic selection models. And because we can fit as a prior the fixed effect using the additive Bayesian model. Okay, full disclosure, I am not familiar with the additive Bayesian model. If it's something like Bayes A or Bayes B, maybe, I mean, my expectation is that switching to a Bayesian approach is not going to be a magic bullet that's going to no longer make us observe those results. So my hunch is that the answer is no, but I would love to be shown wrong, as I have with this result. Are there other questions?
In this genome paper, did any simulation that did not simulate metastasis?
Right.
Is that something that I know when you're you can include as a fixed effect peak markers from GWAS in order to identify metastasis
Yeah.
with other markers? I'm just trying to kind of reconcile that with what we're seeing here in the genomic selection context.
Yeah. Okay, so this is a fantastic point. So the first part of the question is, did we simulate epistasis here? No, we did not simulate interaction effects between genes. Like, it was strictly additive. So then the second part is, what happens if we were to include epistatic effects as fixed effect covariates? Would we see this result we're observing on prediction on page 15, where we see a drop in prediction accuracy? I would say this, okay? Here's my speculation. If the epistatic effect that's being quantified in your training set is the same epistatic effect that is present in your prediction set, then I think that you're going to see an increased prediction accuracy. And then if that prediction set does not have the same epistatic effect, I would speculate that you see something similar to this. Great question. And by the way, I love epistasis. Okay. Let's see. Are there other questions?
What is a QTN?
What is a QTN? Right, that is an acronym. I snuck into this presentation and I told nobody what it is. So a QTN is a quantitative trait nucleotide. Okay, so I use it within the context of simulation studies. So let's say we have a data set of SNPs, okay? And I randomly select a SNP and I assign an additive, dominance, or epistatic effect to it. And it results in your observed phenotype after adding normally distributed error. So the SNP that I randomly select to have an effect size is a QTN. And yeah, that's the answer to the question. Let's see, any other here? Okay. Would use only markers located in genes help GS predictions? Okay, so that question is, if we used markers only in genes, would that help genomic selection predictions? So not necessarily, okay? So would you all agree with me that not every single SNP inside of a gene is causal? Okay, so if I had a whole bunch of causal SNPs in the gene, and I use that only to make predictions, I would not expect to see, higher prediction accuracies than others. So that's my first answer. My second answer is that, I would need to talk to my molecular biologist and functional biologist colleagues, but my understanding is that causal mutations can be inside of genes and they can be also outside of genes, right? Like maybe in like chromatin regions or something. So if we only focus on SNPs and genes for genomic selection, I would argue that we're missing the stuff that's not inside of genes. So that's my answer to that good question. Let's see. Yeah, are there other questions? Okay, you're welcome. Thank you. The person. Oh, wait, can you see it on chat? No. Okay. The a person on chat wrote thanks, so I say you're welcome.
Thank you.
Yeah. Hey, you're welcome. And also that happened in class, right? So are there any more questions? Okay. Going to give them another second. Okay, so what I'm going to do is this. I'm going to end this presentation, and I'm going to tell the people who are here in person some good restaurants in Champaign-Urbana to go to for dinner. And then I'm going to share the Zoom link. Oh, here we go. Why significant selected markers gave higher accuracy? Okay, okay, so the question is, why? Okay. So this significant selected markers, so the peak associated GWAS markers, they gave higher, well, in this picture here, we see that most of the time they do not give higher prediction accuracy. I think for a peak associated GWAS markers to yield higher prediction accuracy, okay, in an independent set of data, it needs to be either the causal mutation or it needs to have the same amount of LD with your causal mutations. Okay, so I'm going to call it a day and I'll tell you all where to go to for dinner. And everybody listening online, thank you so much, especially those of you in a time zone where it's like maybe 4 in the morning. I really appreciate you tuning in. I will be happy to answer follow-up questions, and my inbox is full of questions. So if you don't hear back from me in a couple of days, send me a follow-up. I'll be happy to follow up. Okay. All right. Bye-bye. Okay. So let me end this Zoom meeting. Here we go. Okay.